Hi everyone. In today's lesson, we're going to be taking a look at what is meant by optimizing a situation. So in your notebook, please put down today's subtitle, Optimizing a Situation. Well, if you check a dictionary, you'll find that the word optimizing or optimization is often linked to the definition of making something better. While in math, optimizing means exactly that. It's to take a certain situation and to make it better. Well, what kind of situations are we talking about? Well, the situations that you'll be handed down will involve a very specific rule or equation, and your job is to calculate the largest numerical value for that rule, in a case such as generating profits for a company, or your job might be to calculate the smallest numerical value, such as in the case where a company would like to reduce production costs. The big question in your mind might be, what kind of specific rule are we talking about? Well, the rule is different for every situation. So let's take a look at an example of a company whose rule we'd like to maximize. In our example, suppose that Sony has a stock of PlayStation 3s that sell for $400 and a stock of PlayStation Portables that sell for $200. Sony would like to maximize its revenue from these two products. To create a rule for the situation, first we must define our variables. So suppose that I set the PlayStation 3s to be X and a number of PlayStation Portables to be Y. In this case, the rule created from this situation using these variables would be that the total revenue would be equal to 400 multiplied by X, because a PlayStation 3 sells for $400 a pop, plus the money generated from selling the PlayStation Portables. So that's 200 multiplied by Y. And for Sony, this is the rule that they would like to maximize. Sell as many PlayStation 3s and PlayStation Portables as possible in order to create the largest amount of revenue. But now, having the rule in front of you, the big question in your mind might be, where do the values for X and Y come from? Well, that's easy. They actually come from the vertices of the polygon of constraints. Therefore, in order to understand the rest of this video, you must already have prior knowledge of polygon of constraints. If you don't, please refer to the video in my collection which discusses the polygon of constraints. With that being said, you should be aware that in order to determine the vertices of a polygon of constraints, we need a system of several inequalities. So the next question on your mind might be, where do these inequalities come from? Well, they come from the constraints that a company like Sony might place on their inventory of PlayStation 3s and PlayStation Portables. The constraints may be the following. It could be that Sony requires that they have at most 90 systems in inventory. They may also require that they have at least 50 PlayStation 3s. The third constraint that you notice might be that Sony needs at least 20 PlayStation Portables. And the final constraint, which you may notice, could involve that the PlayStation 3s must be at least double the number of PlayStation Portables. With these constraints in front of you, you can easily form a system of inequalities which will lead you to determining the polygon of constraints. So, without further hesitation, let's form the system of inequalities corresponding to these four constraints. I'll be doing some of them in a different color so that when it comes time to determining our polygon of constraints, visually it'll be easier to detect our different lines. First, let's start with the first constraint. It states that Sony would like to have at most 90 systems in inventory. Well, this leads to our first inequality, which is quite simply X plus Y has to be at most 90. Next, The second constraint states that Sony would like to have at least 50 PlayStation 3s. So, this leads to a very easy inequality of x must be at least 50. Next, the third constraint states that Sony would like to have at least 20 PlayStation Portables. So this leads to a very easy inequality of y has to be at least 20. And the final constraint states that the number of PlayStation 3s has to be at least double the number of PlayStation Portables. This leads to the inequality x has to be at least the double of y. And to end the system, there are two rules that are required, although they are unwritten. Keep in mind that when we're dealing with solid objects, they cannot be allowed to be negative quantities. Therefore, we must insert two inequalities that are unwritten, and they will have to be inserted in many of the situations. They are that x has to be bigger than or equal to 0, and also y must be bigger than or equal to 0. We cannot allow the number of PlayStation 3s and PlayStation Portables to be in a negative quantities. That logically doesn't make sense. And here we have it. We have a system of 6 inequalities. You can already start seeing how long this procedure can be, because when it comes time for graphing, we're essentially graphing 6 different lines. Fortunately, the legwork that's required may not apply to every one of the inequalities. The way I see it, only the first inequality, x plus y at most 90, and the fourth one, x at least 2y, require any legwork. The other 4 inequalities, x at least 50, y at least 20, x at least 0, and y at least 0, are very easy lines to draw without having to go through any legwork. So without further hesitation, let's do the legwork required for solving x plus y at most 90. As with any straight line, you're free to use whichever technique you want in order to draw a straight line. I'm going to simply plug in some random x's and or y values in order to get myself 2 points for drawing our straight line. So, completely randomly, what if I decided that x was 0? Let's see what happens to the y value. So we have 0 plus y is equal to 90. Therefore, y is equal to 90. And that gives us 1 point on that line, located at 0 and 90. Let's get a second point. How about if y was 0? Let's see what happens to the x. So we have x plus 0 is equal to 90. Therefore, x is equal to 90. And that gives a second point for drawing our straight line, located at 90 and 0. And finally, let's test a completely random point on a Cartesian plane in order to determine where we should be shading. The point 0, 0 is not on this line, therefore it makes 0, 0 a very convenient test point. Regardless of whichever point you choose, you must let me know. So, I will be testing 0, 0. Let's see what happens to our inequality. We have 0 plus 0, smaller than or equal to 90, and therefore 0 is smaller than or equal to 90, and that produces a true statement. Therefore, our shaded region for this inequality will be the region that contains 0, 0. Next, let's go through the legwork involved in solving for this inequality. X has to be at least 2y. So going through all the same procedure, let's find out 2 points so that we can draw our straight line. First, let's try if completely randomly x was 0. Let's see what happens. So we have that 0 has to equal to 2y, and therefore y is equal to 0. So therefore, one possible point on the straight line is located at 0 and 0. Now, let's find another point. Notice that 0, 0 is on this line, and therefore I cannot try y equals 0. I have to try something else. In this particular scenario, it's very easy to pick a nice y value to use. How about if y was equal to 10? Let's see what happens to our x value. So we have that x is equal to 2 multiplied by 10, and therefore x is equal to 20. And that gives us a second point, which is located at 20 and 10. And finally, for our test, unfortunately 0, 0 is located on this line, so that makes 0, 0 not an appropriate test point. So pick another test point on the Cartesian plane. How about completely randomly, I choose to test, how about 10 and 1? Let's see what happens to our inequality. So we have that 10 is bigger than or equal to 2 times 1. So 10 is bigger than or equal to 2, and that creates a true statement. Therefore, the shaded region for this inequality will be the region that contains our test point 10 and 1. Now it's time to draw. In order to accommodate all the information in this problem, you'll need a grid that's about this size. And as you're preparing your grid, please pay attention to the axis labels. They must match the decision about your variables all the way at the beginning of the scenario. Based on our decision, our x-axis was a number of PlayStation 3s, and our y-axis was a number of PlayStation Portables. So go ahead, pause the video, and prepare your grid now. Alright, with your grid ready to go, we can draw the lines corresponding to all 6 of our inequalities. It might seem like it's going to be a lot of work, but luckily for us, drawing the x-axis and the y-axis themselves already take care of 2 of the inequalities. X at least 0 and y at least 0 are already taken care of. This is because, remember, those 2 inequalities guarantee that the number of PS3s and the number of PSPs never dip into the negative quantities. Well, with the first quadrant only, it already guarantees this. So we basically have to take care of the other 4 inequalities. So without further hesitation, let's take care of the first inequality with which we did the legwork. X plus y at most 90. We found that we had a point located at 0 and 90, right there. And we had another point located at 90 and 0, right there. And of course, using your semi-artistic skills, you should be able to draw a line that looks like that. And thanks to our test point of 0, 0, we determined that the shaded region is a region that contains 0, 0. So I'm going to draw my arrows pointing to that region. Next, let's draw the line corresponding to the other inequality with which we had to do the legwork. X has to be at least 2y. We found that one point was located at 0, 0, right there. And we found completely randomly that another point was located at 20 and 10, right about there. And once again, using your semi-artistic skill, you should be able to produce a line that looks like that. And thanks to our test point of 10 and 1, which I remind you was chosen completely randomly, we found that the shaded region corresponding to this inequality is the region that contains our test point 10 and 1. So I'm going to draw my arrows which correspond to this shaded region. Here we go. 2 lines down, 2 lines to go. Let's draw the line that corresponds to the inequality x has to be at least 50. So the equation x equals 50 should produce the following line. And to handle the inequality of x having to be bigger than 50, this tells us that the shaded region is on this side. So I'm going to draw all my arrows. So this means that anything to the right of this line is bigger than 50, which is what we need. And finally, the last inequality, y has to be at least 20, is shown with the following line. And to handle the inequality of y having to be bigger than 20, this means that it's everything above that line. So I'm going to draw my arrows to show that. And there we have it. All of our 6 inequalities are shown. To determine the polygon constraints, you need to train your eyes to detect where the common region is for all of these inequalities. If you look very carefully, it appears that all the arrows are converging to this particular polygon, which I will highlight in pink. There we go. This appears to be the region that is common to all of these inequalities. And finally, let's identify the vertices that belong to this polygon. The first one is right here, and that is located at the coordinate 60 and 30. And of course, this is assuming that you drew everything correctly. The second coordinate is located right here. And that coordinate is 70 and 20. The third vertex of this polygon occurs right here. And if you drew your graphs properly, that coordinate corresponds to 50 and 20. And the final vertex of this polygon is located right here. And again, if you drew it properly, that corresponds to 50 and 25. As you can imagine, if you get even one line wrong, it will affect many of your results. With all our vertices of the polygon constraints clearly identified, it's time to finally figure out which of those vertices will help Sony maximize their revenue. Remember, all the way at the beginning, the rule for the revenue was the following. PlayStation 3s at $400 a pop, and PlayStation Portables at $200 a pop. So, your final procedure will be to test each of the vertices into the coordinates x and y, and see which one of those maximizes the revenue for Sony. So first, let's try, how about the vertex 50 and 20? Let's see what happens. So the revenue we'll get will be 400 times 50 plus 200 times 20, and that will give us a revenue of $24,000. Next, let's try another vertex. How about for 50 and 25? That will give us 400 times 50 plus 200 times 25. And that will give us a total revenue of $25,000. Next, let's try testing the vertex 60 and 30. That will give us 400 times 60 plus 200 times 30. And that will give us a total revenue of $30,000. And finally, let's test our fourth vertex, located at 70 and 20. So that gives us 400 times 70 plus 200 times 20, and that gives us a total revenue of $32,000. And based on these results, this leads us to the conclusion that Sony must sell 70 PlayStation 3s and 20 PlayStation Portables in order to maximize revenues while satisfying all the company's constraints. And this is what is meant by optimizing a situation. It's not difficult, but yes, sometimes it can get horribly long. And that's all there is, ladies and gentlemen, to optimization.